Hello, welcome to the technical demonstration of my modular visual algorithm analysis program. The purpose of said program is to provide an interactive visual for comparing sorting algorithms. In this video, I will be demonstrating three common sorting algorithms most computer scientists will be familiar with. Those being bubble sort, which is the least coding complexity and generally the first sorting algorithm one will learn, but consequentially has one of the worst time complexities at big O of n squared time. The next would be shell sorting, which is a variation on bubble sort with some optimizations. That is also big O n squared time and of more moderate coding complexity. And lastly, merge sorting, which is one of the most optimal sorting algorithms at big O n log n time, but has the highest coding complexity of all three. Here you're seeing bubble sort work on a small data set of 10 elements. Notice how the algorithm repeatedly steps through the list, comparing neighbors and then swapping them whenever they're out of order. Even with only 10 items, you can already see the signature bubbling effect as the largest values drift toward the end one pass at a time. We will use this same data set across all three algorithms. Bubble sort is relatively quick when sorting a small collection of elements like 10. Now, notice the comparison count here is 44, and time to completion is 22,051 milliseconds. This is heavily skewed due to visual delay. There's a slider you can see there is set at 500 milliseconds. The reported time is heavily inflated because each visual update adds a 500 millisecond delay to make it visually easy to understand. So just keep that in mind as we move forward. Now with shell sort, the movement looks very different. Instead of comparing neighbors, shell sort starts with comparing elements that are far apart, using a gap that shrinks over time. This lets the algorithm quickly reduce disorder across the entire list. As the gap gets smaller, the list becomes almost sorted. So those final passes happen much faster. Notice the difference here. The comparison count is 28 and time to completion is 16,028. When merge sort runs, you'll see the list repeatedly divide into smaller sublists. Each half gets stored independently, then merged back together in order. The merge step creates a very clean, structured movement, bars flowing into place as two sorted halves combine. Unlike bubble or shell, merge sort doesn't rely on repeated comparisons inside the same region. Instead, it organizes the data through divide and conquer, which gives it consistently fast performance even on much larger lists. However, the comparison count here is 21 and time to completion is 17,030 milliseconds, which isn't much faster on a smaller data set than either bubble or shell sort. This is because merge has a higher overhead on small lists than shell and bubble sort due to it recursively dividing up the data set. Next, I'd like to move on to seeing what these algorithms do if the data is already sorted. So when we run bubble sort on a sorted list, it becomes extremely efficient. Since all neighboring pairs are already in the correct order, the algorithm completes a single pass, makes no swaps, and stops early. Take note of the comparison count here, only 9. Now, when we run shell sort on the already sorted data set, notice that it performs more operations than bubble sort. Shell sort is always performing its full sequence of gap-based passes, and even when no rendering is needed, this is causing more comparisons to occur. So we see that we are at 22 here. When we run merge sort on the already sorted data set, it also performs more operations than bubble sort. Like shell sort, merge sort follows the divide and conquer process, recursively splitting and merging the data regardless of whether it's sorted. This results in 19 comparisons, which is still efficient, but clearly not as fast as bubble sort on a best case input. Now, let's scale things up a bit. I've changed the data set to 100 elements, again using the same underlying data across all three algorithms. But notice here, for bubble sort, the behavior we saw with 10 elements becomes much more dramatic. The algorithm still works by repeatedly sweeping through the list, comparing and swapping neighbors, but now there's far more work to do on each pass. You'll see the bars churning slowly as large values bubble toward the end over many, many passes. On this 100 element list, bubble sort needs 4,814 comparisons and takes about 28,860 milliseconds, with the visual delay being sped up to 5 milliseconds as well. This clearly shows how quadratic n squared behavior starts to become inefficient as the input size grows. Shell sort on the same 100 element dataset looks noticeably more efficient because it begins with a larger gap and compares elements far apart. It quickly reduces the overall disorder before tightening the gap and doing a more localized fix. Visually, you see the list becoming mostly sorted fairly early, with the final passes cleaning up rather than doing all the work from scratch. On this input, shell sort uses 878 comparisons and finishes in about 5,566 milliseconds, which is a significant improvement over bubble sort, even though both have big O n squared worst case complexity. Merge sort behaves differently, still on this 100 elements. The list is repeatedly split into halves, sorted, and merged back together. On the visualization, you'll see deep recursive structure, many small sublists forming and then flowing together into larger sorted segments. Even though there's more overhead in terms of function calls and merging logic, the total work grows on the order of n log n, which scales much better as n increases. For this data set, merge sort completes in 544 comparisons and about 3,964 milliseconds, making its efficiency advantage much more apparent than on the tiny 10 element example. Here's a bar graph to better illustrate the differences between the comparisons in blue and the time to process in red. You can see how bubble sort is incredibly inefficient relative to its counterparts. So, what's next? Well, let's see what happens when these algorithms run head to head against the same data. And look at that. As you may have expected, merge sort is already done. And coming in close second is shell sort, and bubble sort is still working. I'm gonna leave that running as we conclude the presentation. So if you'd like to contribute to this project, you can do so by accessing the GitHub repository at github.com/henry-thebinarybuddies /algorithmanalysis.git. You'll see that on the screen there. I intend for this to be a living project and will likely be refactoring it very soon and adding some more algorithms over time. Once you've downloaded the project, you can run the driver class that's nested in the source folder. It's titled Algorithm Analysis Driver. Currently, the program is intended to be written in a model view control pattern, but requires a lot of refactoring before it can be considered traditionally as such. That being said, depending on when you're viewing this video, that may already be resolved. So here's a brief list of my references in case you'd like to investigate further. But without further ado, I want to thank you for viewing my presentation, and I hope that you're interested in maybe contributing to the GitHub repository with maybe some algorithms that you would like to be able to visualize. Again, my name is Henry Rudolph, and this is my algorithm analysis project. And look at that. Bubble sort has finally finished, and its comparisons are 19,845 with a time of 116,954 milliseconds. So, as expected, terribly inefficient.